Today we're going to look at classical viewing, and that'll get us into a longer discussion over the rest of this week, next week, about how we do viewing using the synthetic camera model. But it helps to have a picture of what the classical views are, how they were obtained, if for nothing else, to appreciate what you might be asked to do to create a certain view, but also the kind of techniques that were created to create particular kind of views, and how it's the same and different when we do it with computer graphics. So we're going to introduce these views and using our basic image formation model, but look at the kind of views that architects, engineers, artists have, and each one has a purpose. I mean, if you ever had to take a drafting class, you probably first did multi-view orthographic projections. They're used in constructions, and whether you've created them yourself or not, I'm sure you've seen them. Then there are perspective views that look like the real world, or at least give that real world feeling, so that things far away are smaller than things that are closer to the viewer. And each one has its own benefits, and each one has some drawbacks when you try and actually construct it or in its use. So let's start by looking at the basic elements, and the elements are kind of what we had in our original picture of how we did image formation. We had some objects out there, and we had a viewer or a camera or some other optical device which was looking at those views. And then what we did to construct the actual image was to use projectors that went through the center of the lens if it was a camera, or the center of projection for a perspective view. And if we also are going to look at parallel views, where those projectors become parallel to each other instead of all converging at a common point. Now, classically, views were based on relationships among these objects, in particular between the object that you might be trying to view and the viewer. And each type of view is based on a particular orientation or combination of the parameters of those two. Now, that's in contrast to what we've tried to say with computer graphics, that we're going to have, these things are going to be independent. We're going to specify the objects independently of where we place the camera and the properties of the camera, which is a much more physical perspective to this. But for literally thousands of years, the idea has been to get certain kinds of views by orienting an object relative to a camera or an artist, or having the artist or camera be placed where it is in relation, at a special place in relation to the view. Now, a lot of this is based on the idea that objects are constructed from a bunch of flat polygonal faces, which we can think of, at least if we're talking about things like buildings, as being the principal faces, like the front, the back, the sides, the top view perhaps, and in some applications perhaps an underneath or a bottom view. If you have something like a sphere, obviously there's no notion of a principal face because it looks the same wherever you put it. But the development of viewing was really based on these ideas that you were looking at these kind of rectangular-like shapes, and that we could identify certain principal faces and say, I want to look at the front, I want to look at the side, I want to look at the top. And the kind of projections that emerged from that were known as planar geometric projections, and each of those words has a very special meaning because there are many other types of projections. But generally, the idea is that your projectors are always going to be lines, and for what we do, they're going to do one of two things. They're either going to converge at a center of projection, or they're going to be parallel to each other. One of the things we'll see, although we're not going to take that path today, is that that parallel projections are the limit of having a perspective projection with a center of projection. And as you move that center projection further and further away from the objects, anyone who's standing close to the object sees those projectors becoming more and more parallel. And so in the limit, when the center of projection moves off to infinity, you get parallel projectors going in a particular direction. But what we're going to do both in our computer graphics, or at least today, and in our traditional classical views, is to look at them as being two different ways of doing viewing. Second, that we want to preserve lines. That planar geometric projections, the geometric is really with respect that a line in the object is going to project into a line in the image. That will preserve it as a line, but it will not necessarily preserve angles. So it's not necessary that a square project into a square. It'll project into something where the lines on the edges of the square, its perimeter, each of those lines will be still a line, but it may project into, for example, into a parallel piping. Okay. Now, there are lots of non-planar projections that you are actually familiar with. All you have to do is look at an atlas, and you'll see all of these different maps and different ways of displaying data. And these can't be planar geometric projections if they're forming images of the surface of the Earth, because if you have a sphere, you cannot project that sphere into, say, a two-dimensional rectangle and with a planar geometric projection. Something is going to have to be distorted, and I think you're all familiar with that. If you look at the standard Mercator projection, you see these enormous distortions at the poles, and the stuff around the equator looks a lot better. But that's just one way to do that, and if you look at a good atlas, you'll see many other ways. But all of those are non-planar projections, and we're going to worry only about the special class of planar geometric projections. So here's a picture of 6 classical views, and you can start to see some of the differences. So here's what's called a front elevation. We have a model here goes back to my original edition of a little Greek temple that my wife did, and it's sort of an homage to the Greeks, who really understood all of these principles and how things projected in order to get things that had proportions that were aesthetically pleasing. So here's a front elevation of that temple, and notice that you're only seeing the front face of the building. That's again the notion of a principal face. This is the front face. Now, if you want to see more, because one of the problems here is we're not seeing the whole thing, is you have oblique projections, and here's a particular one that's called, architects call an elevation oblique, where you notice that you've preserved the front face and you've changed some things on the side. Lines, notice, are still preserved as lines. These are indeed planar geometric projections, but there's some distortion of angles here, because this was a right angle, but it's certainly not a right angle when it's projected. But you have preserved angles in the front face. What's called a plan oblique to an architect is that you're looking down at it, but you've somehow distorted the view so that you still see 3 of the principal faces, the front, the side, and the top, but you've actually preserved shapes in the top. Notice that the base here, you still have right angles. Well, now the angles in the front face are no longer preserved as right angles. So it depends very much on what you want to do, but in both of these you're getting to at least see 3 of the principal faces. Now, this one over here is a fairly familiar one, or will be in a little while. This is an isometric. It's another type of parallel view. These are all parallel views here, these first 4. And notice here you're seeing 3 principal faces. It perhaps looks a little more realistic than these do, but all of the angles have been varied here. Right angles have not been preserved anywhere. But an isometric is a very standard thing to display when you're doing things like in CAD, if you're designing a mechanical part, if you're an architect working with the design of a building. An isometric is a very standard form to use. Now we get to the 2 of the perspective views. This is called a one-point perspective. We'll define it a little better in a while. But notice in this particular one that distances far away are shrunk. That diminution of size is the term. We'll You'll see that in a minute. And so it looks perhaps a little more realistic. It's a one-point perspective because the lines in the front face and on the top are still parallel to each other. These are remaining parallel in this, say this is the x direction, and lines in the y direction are parallel. But now parallel lines in the z direction all converge at a point which is why it's called a one-point perspective. Now here's the most general case, is called a three-point perspective. And if you look at this, the lines in the principal directions, the x, y, and z directions, along the front, the side, pointing up and down, all converge. So in the y direction, they're converging down here to a point. In the z direction, they're converging back here on the top right. And in the x direction, there's another convergence going on somewhere back over here on the top left. And that's known as obviously as a three-point perspective. Now notice, well, we may not be able to notice that these have the advantage of perhaps looking more realistic. This is maybe perhaps a little exaggerated. We don't have to exaggerate it as much. But these are going to be a lot easier to construct if you're doing it by hand. So the difference here in parallel perspective is that computer graphics, we're going to work things out with our projection matrices so that all of the parallel projection or perspective projection are going to be carried out exactly the same. And that's nice because then we won't have to have a separate pipeline for the parallel projections and a separate pipeline for the perspective projections. But in classical viewing, techniques are completely different for drawing each type. And that really is a basic difference between a huge advantage for computer graphics because we don't have to worry about, oh gee, how do I do this three-point perspective? How do I construct an isometric? And that's really fundamental to everything we're doing. And we're not going to worry about that the parallel view is the limit mathematically of the perspective view. So we really wind up with a taxonomy somewhat like this. It says, of our planar geometric projections, I'm going to divide them into two classes, the parallel projections and the perspective projections. And then what I'm going to do in the next bunch of slides for parallel is see what is to take the most restrictive case first, which is going to give me the multi-view orthographic projections, and then start saying, what if I release this restriction? Then I'm going to wind up with the axiometric views, three types. And if I take another restriction away, I'm going to get the oblique views. And those are like the plan oblique we saw in a couple of slides ago. For perspective, generally we'll just define what a 1 and a 2 and a 3-point perspective are. But first let's look at those, at the different projections. First let's look, here's just sort of summarizing stuff we've covered in a number of ways, is what a perspective projection looks like sort of graphically. Is we have our center of projection, we have a projection plane, and we have the projectors drawn from the center of projection. And where the projector pierces that projection plane is where we have the image of that point. So the point in the back right corner here pierces the plane here and projects to this point over here, and likewise for the others. Now there's a lot of flexibility in what you can do here. You can move the object around, you can move the projection plane. So how do you orient the projection plane with respect to the object is going to be important, and certainly where we place the center of projection. Now parallel view, all we did was move that direction, that center of projection out to infinity. So now we kept the projection plane where it was before. The projectors are now parallel to each other, but we have a very similar thing. We have projectors now, and where they pierce the projection plane is where we have the projection of, say, this point projects into this point over here. But we also still have the flexibility to change the direction of projection, to change the orientation and location of the projection plane, and then place the projection plane and the direction of projection in some way relative to one or more principal faces of the object. At least that's the classical way of looking at it. So now let's look specifically at the parallel projections and start with the most restrictive case, which is the orthographic projection. Okay, so Orthographic means perpendicular or orthogonal. And what we're going to do is position the projection plane so it's parallel to one of the principal faces of the object. Okay, so the idea here is that in this example, what I want to do is view this particular principal face, and so I'm going to place think of this as the back of a camera. If I want to take a picture of the front, I'm going to try and have that camera placed so the back of it is parallel to that front face. Now that's going to mean that the projectors for a orthogonal projection are orthogonal to that plane. So they're locked to this plane. So if I change the orientation of this plane to look, say, at the side view, I'm moving the projectors too because they're staying orthogonal to that plane. And go back a second, my analogy with the camera is sort of lacking in that a camera is really always a perspective view. So we're thinking of this sort of limit of the camera where it has incredibly long focal length so that these are almost parallel. But still, the notion is that the back of the imaging system is going to be parallel to a principal face and the projector is going to be perpendicular to it. So with that, you get the standard three views you generally see, because the problem is if I'm going to look at the front, I don't know what the sides look like, I don't know what the top looks like, and so I need more than one, and they're called the multi-view orthographic projections, which give me generally these three views. I'll talk about the isometric in a minute. This is usually the way we would display things, to have the three views and then perhaps the isometric up here to see what they look like. And notice this is also an example when we go back to doing this in WebGL, that this is one of the reasons why you want to have multiple viewports. I could generate all of these different views by changing parameters on my virtual camera, but I want to assign each one to a different area of the display, and that would be why I'd want to have 4 different viewports corresponding to the 4 different views that I want here. Now, let's summarize the advantages and disadvantages of this. Shapes are preserved. This is in the if we look, for example, at the front view, we've preserved perfectly the shape. The angles are preserved here in this projection. The same is true with the side and the top. Now, why is that good? If we're trying to build something, all the measurements are correct. The measurements of angles are correct. The measurements of lengths are correct. Obviously we have to scale it to know what's the difference in size on the screen or on a page or on a paper, but all of the relationships are preserved, including the angles. The difficulty is that we can't really see the whole object, and we try and do things like, oh, well, if I display all 3 of these, I can figure out what the object looks like. Well, maybe you can and maybe you can't, and in fact mathematically you can show there are ambiguities in when you try and figure out what something looks like from 3 views. You can take more views, or you can try and say, well, let's, in addition to having multi-view orthographic projections, let's add something, perhaps an isometric, so to see what it really looks like, and then use these multi-view orthographic projections for our construction documents. So that would be a standard thing, and sort of again illustrates why we need multiple ways of doing it. Now, if we want to see more principal faces of this box-like object, then I'm going to remove the restriction that the projection plane has to be parallel to one of the principal faces. I'm still going to keep the projectors orthogonal to that plane. I'll release that restriction in next example. But in this one, to get what's called an axionometric projection, that the projectors are always still perpendicular, but I now can move the projection plane with respect to the object. So you see the parallel projectors here. You have to accept it, sort of try to draw them so they're perpendicular to this face. Now there's 3 basic types, and the way you can classify them is if you look at a corner, say a corner down here, where you have the 3 principal directions, or you think of, say, a cube where the sides all meet at 90-degree angles. When you project that, you you get something that looks like this. So suppose this was the corner of a cube, it would project like this, and those three 90-degree angles would no longer be 90 degrees. They'd be three angles, theta 1 plus theta 2 plus theta 3. If three of them are the same, or if all three turn out to be the same, which corresponds to placing this plane symmetrically with respect to that corner, that's called an isometric. When two of them are the same, it's called dimetric, and when all three are different, then you say that that's a trimetric projection. But again, it's still an orthographic projection, and which you do depends somewhat on how you would like to view that object. As you'll see here, they give you very different views of the same thing. Here's the isometric, and notice that because, let me back up 1 second. Notice that because these angles have to sum to 180 degrees, there's no way to preserve all angles in any kind of an axiometric projection. So you will in fact preserve distances, although these distances will change depending on what these angles are for your projection, but at least along a given direction, you know that's, for example, 1 inch over here and 1 inch over here correspond to the same length. So they have some potential for doing measurements and construction. Here's the three different views. Notice the symmetry around these corners in the isometric view, and that looks like, where is the projection plane? It looks like it's off symmetrically with respect to this corner at sort of 45 degrees. Here's a dimetric view where the angles are the same on the left and the right, but it's a much shallower angle on the top, and in this one, none of the three angles are the same, and again, it depends what you want to see. This is a nice sort of aerial kind of view of the object. This one is more useful in CAD drawings. So, what's the good in things about this? As we said, the lines are scaled equally in a given direction. That's called foreshortening. Angles are not, as we said, preserved, but you get the advantages. If you have a box-like object, you really do get to see three principal faces in the image, so that's good. There are some interesting optical illusions that happen with this that some people can get very annoyed with, even with some of the examples. If you take a cube and you do an isometric projection of it, a lot of people will see that those lines that are the edges of the cube not being parallel. They'll swear to you that they're converging or diverging. If you take a long, thin object, like say a long, thin cylinder, and you can see the top and the bottom and you project it, those sides that you see, what they're called silhouette edges, will really look like they're diverging as they go further away. And that really annoys some people because it's purely an optical illusion. If you were to measure them on a drawing or to measure them on the screen, they're not diverging, but they sure look that way. They don't look necessarily that real, these projections, because they don't really have what you would see if you were looking at it, where things far away were smaller than things close to you. So there's sort of a halfway measure to getting more realistic applications, but they're very, very useful in CAD. So let's release the one restriction we still have, which is that the projectors have to be perpendicular to the projection plane, and let's say those projectors can make any angle you want with the projection plane, and that's called an oblique projection, which is the most common type. So here I'm trying to show that, again, it's parallel projection. All the projectors are parallel, but they're not striking this projection plane orthogonally. If you look at a top view, you might see something like this. Here's the projection plane that might be parallel to the front face. It doesn't have to be, but suppose it is. Here's the projectors striking the projection plane obliquely. If you look at a side view of this, here's the projection plane again, and here's the projector striking obliquely. A given oblique projection, as you can see from here, is fixed or described by two angles. And you could say they're the angle from looking at it from the top and the angle over here looking at it from one side. There are other ways to do it, but it's a two-angle parameter specification of how oblique it is. Now, there's a couple of things you can notice about that. Is the angles really can be preserved if you do that. If you come back here, I see it there. Look at what's happened over here. We did it in a way that this front face still maintains right angles. Why is that? If you have a face that's parallel to to a principal face and you do an oblique projection, that face, the projection of that face, will in fact have its angles preserved. So you can get something like this. Here's a box with a circle in it. One example is you think of this as a radio, old radio or something with a dial in the middle, or a speaker box where the speaker hole is cut out. If the angles are preserved in this face, then the circle comes out looking like a circle. That's not the case on these sides. So you can still do that. Now, if you look, I probably should have pointed that before. Let me go backwards for a second. If you look at the isometric, if there was a circle on any of these faces, say a decoration, what would they come out as? They'd come out as ellipses. You cannot preserve circles in axionometric projections. So you sort of get the advantage of seeing three faces, but you have the disadvantage of angles being changed or not preserved. And if you have something like circles, they become ellipses, and that just doesn't look right. But here you can at least pick one face, say the front face, and do the obliqueness, pick the oblique angles so that you preserve angles and thus shapes in that particular face. Notice that this has a relation, as we'll see later, to shearing, because it looks like what we did here is we started with a box where all the angles were 90 degrees, and we somehow pulled the sides, the y direction. We pulled that top relative to the bottom. And in fact, when we start getting the mathematical implementation of this through projection matrix, you'll see that it is in fact a shearing operation. But also notice that you cannot do this with any kind of a real-world camera. That's actually not quite true. You need a camera in which the front of it is movable with respect to the back. You have to be able to shear the camera. And if you have an architectural lens, which you can do with an architectural lens, is you can move the front of the lens with respect to the back of the lens. There's a little screw that does that. And what that will let you do is what you want here. Because if you take a picture of a tall building, the problem is when you look at that, you have to tip the camera backwards to capture that building. And what happens is the sides of the building in the image are not, the edges are not parallel to each other anymore. But with an architectural lens, what you can do is raise the front of it relative to the back of it, and you can actually get the sides of that building to be parallel to each other. And that's important if you're trying to get this accurate photograph of the building. An old bellows camera has even more flexibility, because the reason you have those flexible bellows sides is you have complete ability to move the back of the camera with respect to the front of the camera and then get these kinds of effects. Computer graphics, we just set a parameter and we can do all of these things. Okay, now let's turn to perspective. And perspective in some sense is easier to talk about, just the difference between what's 1, 2, and 3 points. So back to this image, we have all the projectors converging at the center of projection, which is the eye. And now we can place this projection plane and the viewer wherever we want. Now we saw that what will happen in the perspective projection is that parallel lines will now converge because distances further from the viewer are being compressed or made smaller, which is called diminution of size. And so parallel lines will now appear to converge at a single point. If there's one point where for our box-like object they converge, that's a one-point projection that preserves parallel lines in the two other directions, a 2-point perspective would have lines in two of the principal directions converging, and likewise a 3-point projection would do. So that what that means in terms of where the projection plane is, a 1-point perspective, the projection plane is parallel to a principal face. In a 2-point projection, the projection plane is parallel to one direction, like this, like say this corner over here, and if there's no relationship, you get a 3-point projection. Now, the problem with this is, and I can see it here, I'll come talk about it again in a minute, is it really doesn't preserve distances. So even though in an axionometric projection you get foreshortening, equal distances along this direction of projection here, along a projector, are equal in the image as they are if they are in the actual real world. Here the problem is that 1 inch here in the projection is not 1 inch that corresponds to a distance which is very different than 1 inch over here. In fact, as you get closer and closer to the vanishing point, something like 1 inch will correspond to an almost infinite distance over here. So you really can't do any kind of real measurements off of a perspective projection, except perhaps in this plane where you maintain two directions as being parallel. So to sort of review, here's the 3-point perspective. No principal face is parallel to the projection plane, and you get the three vanishing points for the three principal directions, which you could sort of draw out here by just sort of following these lines that were parallel in the object. A 2-point perspective has two of the directions converging. So in this example, there's no convergence of lines in the original that are going up and down, but the other two directions have, there's a vanishing point out here and there's a vanishing point out here to the right, and the 1-point perspective preserves angles in one principal face, that is where the projection plane is parallel to that face, and there's only a single vanishing point in this example. Now, if you were doing this as if you were a painter or a sketcher, you'd actually might put those vanishing points on the image and on your painting or on your paper, and then learn how to draw backwards to construct this object. As far as we're concerned in computer graphics, there's either a perspective projection or there's a parallel projection, and wherever the vanishing points come out, they come out of doing the mathematics right rather than. So that's a huge second advantage to this. So, sort of summarizing advantages and disadvantages of this perspective view, things that are further away look smaller. That's what creates the realism in that, but the distances along a given line are not equal unless that line is in a face parallel to the projection plane. That's known as non-uniform foreshortening, and the only place you're going to preserve an angle is in a plane parallel to the projection plane. So, and as I said a minute ago, this is the most difficult to construct by hand, but in doing it by computer, none of these projections are more difficult than any other one. We simply set the parameters that describe the camera, we describe our objects, we do the projection, and out comes that image. Now, the difficulty with it, from the perspective of someone who's, say, used to doing it, say an artist or an architect, is it's very difficult to get the relationships between the object and the viewer, because everything we're doing by computer is based on this idea that all of these specifications are independent of each other. So if I say, I want you to give me a 1-point perspective of these objects that we just designed with our CAD system, you're going to have to somehow figure out what should be the proper parameters for setting your camera. So essentially, you've got to go through a difficult, perhaps, procedure to now figure out what do I do to get that particular image. So you're sort of giving up something in not being able to have a system, and pretty much none of the graphic systems do this, where you have a way of representing a relationship between the viewer and the objects that the viewer is seeing. Okay, so now we're going to, next lecture, start turning to how we do this within WebGL.